Okay, so this is a combination of lessons 7 and 8. First, we'll be drawing Lewis dot diagrams for covalent compounds. And second, we will be determining the polarity of molecules. So the objectives for these two lessons will be to learn how to draw and illustrate the sharing of electrons through the Lewis dot diagram for covalent or molecular compounds. And also you will be required to describe how covalent bonds form and identify bonds as either being polar covalent or nonpolar covalent. And you'll also have to determine whether a molecule is polar or nonpolar. So let's look at Lewis dot diagrams for covalent compounds. An animation will be located at this website, so please go to this when you get a chance. Write the element symbols and draw their valence electrons. If there are more than two atoms, place the least electronegative in the center. So what do I mean by this? You have to look up the electronegativity values in your reference tables. Okay, and here's an example of water. Now in water, hydrogen is going to be the least electronegative, so we would start with one hydrogen, and we have another one, and then our oxygen. So first we'll have to draw out how many valence electrons are in each, and each hydrogen has 1, oxygen has 6. What I'm going to do is, just for dot diagrams for bonding, I'm going to pair as many as I can first, and then whatever's left will count as how many bonds it can form. So for the 2 electrons that are unpaired, that means that oxygen can form 2 bonds. Okay, so the first step after we do this, what would be the second step obviously, is to basically illustrate this through a structural formula. And we use dashes for that. So for step 2, we'll draw dashes or lines between the elements connecting all lone electrons. Your goal is to pair up all unpaired electrons. All right. So again, hydrogen has, I'm going to put it over here, 1 unpaired. This hydrogen has another unpaired. And then our oxygen has 2 spots here. Okay, so when we're going to draw this out, basically what I'm going to do is I'm not going to put the 2 hydrogens next to each other, but I'm going to rearrange it so that I can show that the hydrogens will be sharing electrons on either side of the oxygen. Okay, and also another way to do this then will be to draw it this way as well. So the dashed lines represent a share of 2 electrons here. Okay, so one dashed line is called a single bond. So for example, we have here a bond between 2 carbons, and then we also have all of these empty spots here, which will allow for sharing of 2 electrons. So if we put hydrogens in there, this would be C2H6. Okay, and basically what we're indicating here is that there's a sharing of 2 electrons on either side of the carbons. Okay, so each line will represent 2 electrons. So the number of electrons being shared between the carbons is 2, between these 2 carbons. Number of electron pairs being shared between the carbons will be 1 electron pair. Okay, so that's the difference. Pairs and how many. So each pair is equal to 2 total electrons being shared. Next, 2 dashed lines is called a double bond. And basically this is going to be used when we have 2 carbons and only 4 hydrogen. So this would be C2H4. Okay, so the number of electrons being shared between carbons will be a total of 4, and then the number of electron pairs will be 2. So pairs obviously is going to be the number of electrons shared divided by 2. Finally, 3 dashed lines, go figure, is called a triple bond. 3 dashes equals 3 bonds. And what's happening here is that each line obviously will represent a sharing of 2. So since there's 3, that will tell us that there's 6 electrons being shared between the carbons. And then the number of pairs being shared between the carbons will be 3. And that indicates the 3 lines. So let's draw the Lewis dot diagrams for the following covalent compounds. We're also going to write out their structural formulas, like we saw in the previous examples. Okay, so for hydrochloric acid, we will write out hydrogen with 1 valence electron. Chlorine has 7. Okay, and then these 2 electrons will share. They will share, and we will then draw it out like this. Okay, remember hydrogen can only have 2 valence electrons, so that is indicated by these 2 right here, and then the 8 valence electrons for chlorine to form the stable octet. So those 2 are the ones that are being shared right there. Okay, so now when we draw out the structural formula, it will simply be this. Okay, remember this line, or these 2 electrons, will be represented by 1 dash. Then we have N2, and when we draw out these, nitrogen has 5 valence electrons, and then we'll do the other one. And what we need to show here is that this electron, this one, and this one, and these 3 over here will have to share in order to form the bond. Okay, so if there's 3 electrons, 3 unpaired electrons, that means that there will have to be 3 bonds formed between the 2 nitrogens. So that would show a triple bond. Okay, so that will be our structural formula, and then again, we would do this 1, 2, 3, 1, 2, 3, and then the other nitrogen and the 2 on the ends. Okay, so this would show the 6 shared and then the 2. So each nitrogen will have a total of 8 electrons in their valence shell. Okay, actually what's happening is that's sharing, and then these are sharing. Okay, with a total of 8. That's hard to see. Let's try another one. 3. So we have CCl4, and the least electronegative atom here would be carbon, so that would be the center. But let's just draw out their dot diagrams first. Carbon has 4. I'm going to do this way to make it a little easier. And then we have 4 of these chlorines. 7. Okay, so we're actually adding all of these together to create our Lewis dot diagram. So when we put all of these together here, carbon in the middle, ultimately everything has to have a full or a stable octet, okay? So each chlorine has 8, each carbon has, or the carbon has 8. Again, each chlorine will have 8 valence electrons. So when we draw out the structural formula, a little easier, carbon, and then each set of electrons will be represented by a dash. And the last example, NH3. Some nitrogen in the center with 5. And then 3 hydrogens, so this would come from this hydrogen, and this hydrogen. So in this example, I'm just showing you the X's represent the valence electron from the hydrogen and the fact that these 2 electrons are being shared between the nitrogen and the hydrogens. Right, so when we draw out the structural formula it will look like this. Okay, so let's keep note that the number of unpaired electrons is equal to the number of covalent bonds that can form. For that nonmetal. So for example, I'm just going to give you a couple of things here. We have nitrogen, oxygen, fluorine, let's say over here, carbon, and hydrogen. Okay, and if we draw out their dot diagrams, 4, 5, there's 3 unpaired electrons. 3 unpaired. So that means that it can form 3 bonds with something, okay, like we showed in this example, N, nitrogen, and then 3 bonds, hydrogen, so to form the stable octet. So it's got to share a total of 6 electrons to form 3 bonds. Okay, now oxygen has 7, 2, 3, 4, I'm sorry, 6, 5, and then I'll put one up here, so 2 unpaired, which means that there are 2 bonds formed. Notice the pattern. Carbon, okay? Carbon has 4 valence electrons, 1 on each side, okay, which means that there's 4 unpaired and 4 bonds. And this is always going to be the case. There's nothing else that can happen. Nitrogen is always going to form 3 bonds. Oxygen has to form 2. Carbon has to form 4. Okay. Hydrogen has 1 unpaired. Okay, 1 unpaired and can only form 1 bond with something. That's it. Cannot be like this. Let's say. All right, that cannot happen. So we're going to erase that. And then fluorine, and that we might have myself enough space here, but fluorine has 7. Okay, so 1 unpaired, which means that it can only form 1 bond. Another example, just another one, phosphorus. Okay, phosphorus has 5, which means that there's 3 unpaired electrons right here, 1, 2, and 3, and it can form 3 bonds. Okay, so let's start with polar and nonpolar molecules. Okay, so this begins lesson 8, and remember, molecules are referring to covalent bonds. All right, and there are two different types. There's polar covalent bonds and nonpolar covalent bonds. So just a correction from a previous lesson for the electronegativity difference. Covalent bonds have a electronegativity difference between the bonds of less than 1.7, and ionic bonds is greater than 1.7. Okay, and then what we're going to learn in this lesson is to determine the values for electronegativity differences in the bonds for polar and nonpolar. But also molecules, okay, can be either polar and nonpolar, and their bonds can also be nonpolar and polar as well. And we'll look at that. So a molecule is a covalently bonded substance, always two or more nonmetals bonded together. A molecular compound is also a covalent compound. And I've said that many times before, but this is very important so that when you see molecular or molecules, we're talking about covalent bonds. Now, the shape of these molecules can tell us a lot about the behavior, as well as whether they're going to be polar or nonpolar, and I'm going to give you a little mnemonic in a little bit to help you remember. So polar molecules are asymmetrical. Molecules, which means that there is no line of symmetry, there is an unequal sharing of electrons, and it means basically it doesn't pass the mirror test, can't be folded to reflect itself on either side. So two atoms or two different elements or two different electronegativities. More than two atoms, unbonded electrons or lone pairs around the central atom. Okay, so here's an example, HCl. And what I'm going to do is I'm going to show you how this bond forms, H, with the structural formula, single bond here, okay, sharing of two electrons. And we did this in the previous lesson. So this is a linear shape, and because it's linear going this way, left to right, or we can write it up and down, but this is not symmetrical. If I flipped it, okay, hydrogen would be on this side, chlorine would be on this side. It's not the same on both sides, or if we drew it out this way, it would still not be the same if I flipped it. Mirror image, not the same. Okay, so if we have a nonpolar or a polar molecule, okay, it would be asymmetrical. And here's one example. Another example would be H2O. H2O is polar, okay, and it's going to be bent because there's three atoms, and this is the way a bond or a molecule is shaped when there's three atoms, so it would be a bent shape, we call it. All right, and we would have oxygen, and then hydrogen, and then the other hydrogen. And I drew this out for you in lesson 7. So what's happening here is this is considered polar because oxygen is the more negative element, okay, more electronegative element when we look up the ENDs on the reference table. And so the H's would then have these partially positive charges because this is more negative. So the pull would be toward the oxygen more than it would be toward the hydrogen on the electrons, so they have to share, and it's an unequal sharing. The electrons are kind of pulled more toward the oxygen because of the electronegativity difference or the electronegativity value. Remember, oxygen has a higher tendency to gain electrons because it only needs 2, okay? Versus hydrogen, well, hydrogen only needs 1, but the electronegativity value for hydrogen is less than oxygen. All right, so I do want to indicate here, and it's not in our notes, that a molecule can be polar okay? But a bond can be nonpolar. So a bond is polar if the END is greater than 0.5, and a bond is nonpolar if less than 0.5. Okay, and remember guys, this is greater than and this is less than. All right, I'm just abbreviating it with the symbols. All right, so again, if the electronegativity difference is less than 0.5, but it is asymmetrical, it can be a polar molecule, but with nonpolar bonds. So here are nonpolar molecules, and these are molecules that are symmetrical. There is an equal sharing of electrons, or it does pass the mirror test and it can be folded to reflect itself. So two atoms, generally the same element and the same electronegativities, so that shows that there's no electronegativity difference. END is going to be equal to 0, basically, in this case, or obviously less than 0.5. Okay. So more than two atoms, no unbonded electrons or lone pairs around the central atom. So it's the opposite, obviously, polar, nonpolar. Here's Cl2, two of the same atom, Cl bonded to Cl, okay? Symmetrical, flip it, it's the same on both sides. Chlorine is on both sides, mirror image. Next one, CO2. I'm going to draw that out for you, and carbon, double bond to oxygen. Now this is the thing. In lesson 7, I showed you that oxygen has to form two bonds, and it can't form two bonds with each other when carbon is the central atom. All right, and carbon has to form 4. Okay, notice 1, 2, 3, 4 on the carbon, 2 on each oxygen. So that shows that we have the sharing of these electrons here. Now this again is symmetrical. If I flip it this way, it's going to be the same either way. There are many lines of symmetry here. Okay, there's one here, there's one here. Okay, so if there are two or more lines of symmetry as well, then that means that it is nonpolar. CCl4 now, okay? Again, chlorine will form one bond each. Okay, carbon forms 4. So when we have 5 atoms, it gives us this tetrahedral shape when we draw it out. So carbon will be in the center and then bonded with each chlorine. And we notice that you have one line of symmetry here, one line of symmetry here, and then you have one here and one here as well. So more than 2 lines of symmetry tells us nonpolar as well. All right, so there's different ways that you can tell if a molecule is polar or nonpolar besides looking at the electronegativity values. So here's another way. Remember when I said that the electronegativity difference can show that the bonds are polar yet the molecule is nonpolar. So we need to be aware of that. There are often polar bonds inside nonpolar molecules, so we're going to look back at those previous two examples. Okay, CO2 and CCl4. They're both symmetrical, both nonpolar molecules, but yet if I figure out the electronegativity differences here, the END between the carbon and the chlorine is 0.6, which indicates that it is polar because it's greater than 0.5. Okay, so here, and I'm just going to show you the carbon, electronegativity value is 2.6, chlorine is 3.2. When I subtract those, I get 0.6, and shows me polar bonds, but non-polar molecule. Very important. Okay, so here is the mnemonic that you can use to help you remember this. SNAP. Okay, symmetrical. If it is symmetrical in shape, it is a nonpolar molecule. And if it is asymmetrical, then it's going to be polar. S-N-A-P. So this is for shapes of molecules. And finally, polarity of a molecule can tell you many things. It can tell you, one, how high or low melting point or boiling points will be of that substance. Two, can tell you how easily the liquid form will evaporate. And also, three, whether a substance will dissolve in water. Or some other solvent. We will talk about these in Lesson 9.